Nuclear energy is one of those topics that elicits very passionate responses from people both for and against it. But I am actually not one of those passionate people. I don't have strong feelings one way or the other about nuclear. I tend to ignore it because I live in Australia, and despite being the world's second largest supplier of uranium, we don't have any nuclear energy in Australia, and in fact it's prohibited by law here outside of research and medical purposes. For now at least. But nuclear energy can be a source of zero emissions, round-the-clock, all-year-long energy. And that is a very appealing combination as we race to decarbonise electricity grids around the world. And it's a mature technology, having been a major contributor to some countries' electricity grids since the 1970s. In recent years, however, as other types of electricity have grown rapidly, new nuclear power installations have barely kept pace to replace retiring nuclear generators. In this video, we're going to talk about why that is and whether small modular reactors are a solution to the nuclear industry's problems. We'll be talking with Dr Jose Reyes from NuScale Power about their small modular reactor design. I'm Rosie Barnes. Welcome to Engineering with Rosie. I'll just start by very quickly explaining how nuclear energy works. And probably most of you know as well as I do anyway. I haven't studied nuclear physics since high school, when my favourite teacher stayed back after school to run nuclear physics labs for me and another kid who just couldn't get enough physics from the regular science classes. We had Geiger counters and little samples of radioactive materials. It was so amazing. So shout out to Mr. Philby, the best physics teacher ever. Anyway, currently, all nuclear reactors use nuclear fission to generate electricity. In nuclear fission, you take a big atom like uranium and you fire neutrons at it to get it to split into two or more smaller atoms. The small atoms together weigh less than the big one you started with, and because energy equals mass times the speed of light squared, the reduction in mass means that energy is being released. And as well as energy, neutrons are released, which can then go on to split more uranium atoms, which release more energy, and more neutrons, which can split more atoms, and so on. If you want a slightly more detailed but still very accessible explanation of how a nuclear reactor can keep this chain reaction in balance and control it, then I recommend the fantastic HBO show Chernobyl, which is one of my favourite engineering TV shows ever made. So obviously in Chernobyl they didn't keep things fully under control. The chain reaction led to a meltdown and it caused a massive and tragic accident, which made everyone incredibly aware that nuclear energy is potentially very destructive. If they didn't already know that because of, nuclear bombs and stuff. Now I need to add a but. But nuclear power isn't the only technology with potentially lethal consequences. And when you look at the number of deaths per megawatt hour generated from various energy sources, you actually get nuclear coming out as one of the very safest energy technologies. However, the potentially horrific nature of nuclear accidents makes people worry more about nuclear than the relentless trickle of thousands of deaths each day that occur from air pollution associated with burning fuels. It's not rational, but it's understandable. Then there is also the issue of nuclear waste, which perhaps poses future safety risks, and for sure there are not too many communities who are happy to have nuclear waste stored in their backyards. So both the safety and waste issues cause problems with community acceptance. Nuclear is simply not a popular energy technology with a lot of people, which makes projects harder to develop. And that's pretty much the reason why Germany is planning to retire the last of their fully functioning nuclear reactors by the end of 2022, decades before their useful life is up. And then aside from being unpopular with some communities, nuclear energy in recent years has been held back by high costs and long development timeframes. Take a look at this chart, which shows the change in price for various forms of energy over the 10 years up to 2019. Solar photovoltaics price dropped by 89% in that period. Onshore wind dropped by 70%, combined cycle gas by 32%, coal was pretty flat with a 2% drop. Nuclear was the only one that rose by 26%. And I'll just specify that this is for new build nuclear. Existing nuclear reactors, ones that were built decades ago and have already paid off what it cost to build them, their electricity is quite competitive with other sources. But new build nuclear has not been going well recently. In addition to cost increases, project development timeframes have blown out, with practically all recent and ongoing new build nuclear experiencing delays of a decade or more. So does all this make you think that starting a new nuclear energy company would be a great idea? Well, today I'm talking with someone who has done just that. Dr. Jose Reyes is co-founder and Chief Technology Officer of NuScale Power, who are currently developing a brand new nuclear reactor design. It's a small modular reactor, or SMR. And you may have heard people saying that SMRs are coming to solve all the problems with traditional nuclear energy. Dr. Reyes is going to tell us all about the NuScale design and how they plan to bring to market a nuclear reactor suitable for the modern economy by addressing safety, development time, and cost. Plus the capability to produce hydrogen using high-temperature steam electrolysis, and how they can operate flexibly to suit the needs of a grid with a lot of variable generation and, of course, variable demand. So we'll start with cost. Doesn't this chart paint a pretty pessimistic picture for nuclear? And the further we might try to project into the future, the larger the gap between nuclear and renewables, or even the gap between nuclear with renewables plus energy storage, the larger that gap is going to get. Has nuclear's time simply passed, or can small modular reactor technology start to reverse the direction of this trend?
So this is a great chart, and it's very telling because it's one of the reasons we started our company. we went to small modular reactors because we recognized that there were significant cost savings by doing that. And the first part of it, of course, is the module itself. It's very small. It's all factory manufactured. So that's the reactor vessel and the containment, which is, instead of a big concrete dome, is now just a relatively small steel pressure vessel, which is immersed in water. And that's our concept. It's a reactor inside of an evacuated containment, so it's in a vacuum, immersed in water below ground. And so what that does for us is it allows us to build the plant, to do all the civil construction on site in parallel with manufacturing the modules in a factory. Just doing that reduces the construction time from 5 years down to 3 years. They can be shipped by truck, rail, or barge, depending on the location, from the factory to the site. The second part of that is the level of safety that's offered. And you might not think of safety tied to cost, but in nuclear power today, a lot of the expense of operating a nuclear power plant is tied in the safety systems. By going to this very small module with a relatively small core, only 37 fuel assemblies, everything that you need for safety is right there with the containment vessel, which sits in the pool. So once I isolate that containment vessel, now I've isolated it from the world, and I don't need to add water at all. So in this design, under the worst case conditions, the reactor will shut itself down without any AC or DC power, without any operator action, and it will remain cooled for an unlimited period of time without the need to add water. And so that's the revolutionary breakthrough that we've done, is really in the safety. And we've done it by reducing the number of active safety systems and going to a very simple, passively cooled containment design.
Okay, and is that possible because it's small? Would that kind of thing
right.
be impossible to achieve the same safety mechanism on a large, like Chernobyl-style reactor?
Exactly right. You couldn't. You really can't, because the fact is that I'm using our steel containment shell, which is immersed in water, as a heat exchanger. So basically, if any heat that's released into that containment will get rejected to the pool. Once the control rods fall in by gravity, the power will decay over time. Within a few seconds, you're from 250 megawatts thermal down to about 12 megawatts thermal. After 3 hours, you're down to about 1.5 megawatts thermal, and after 3 days, you're down to about 500 kilowatts of thermal energy that needs to be dissipated. Well, the containment shell, that surface area is so large that just the motion of air at 100 degrees C on the outside of that shell is sufficient to remove all the decay heat. So it goes from it's a very simple approach.
And have you tested that physically?
Yeah. So we've spent about $100 million in testing. We've built facilities all over the world. The integral system test, which were tested some of our key safety systems, was done here at Oregon State University. We built the 1/3 scale prototype and have been running those tests since 2003, actually. So we've got a lot of good data, and of course we've submitted all of that information with our application to the NRC and received the standard design approval back in September of last year.
What do you think about the cost potential? I'm looking again at that same chart, was 2019, so it's a couple of versions old, but that had nuclear power at $155 per megawatt hour, whereas, wind and solar are obviously down around 40. Yeah, how do you see that going forward? Can you ever compete with renewables?
Where we're at right now, this first project with Utah Associated Municipal Power Systems, our target there is $58 per megawatt hour. So that's a target that's been established by the customer, and that does benefit from some production tax credits and things like that. But as we move forward with more modules and more plants, we want to be in that range. It's an opportunity to really develop a standardized module that can be continually reproduced and reduce costs as you develop modules. In that first plant, we will have reduced the cost of the sixth module by about 20% just from learning how to manufacture those modules more completely.
So that is NuScale's approach to cost reduction, which comes in a couple of parts. Reduce manufacturing costs because the size and modularity of the reactors mean they can be manufactured off-site in a dedicated factory. I believe that will be a first. And the other part of NuScale's cost reduction plan is their self-contained, largely passive safety system, which should be less expensive compared to the safety systems in traditional nuclear reactors. But reduced cost is just one part of a profitable project. The other part is the value that's produced. NuScale has two interesting sources of value that I want to talk to Dr. Reyes about: hydrogen production via high temperature steam electrolysis and flexible operation. First, the hydrogen. What was the reason they decided to go down that route? Didn't they already have enough complexity on their plate with a brand new nuclear reactor design? Why did they add in hydrogen capability as well instead of, just supplying electricity to someone with a regular electrolyzer to make garden variety green hydrogen?
So for commercial scale, what we've learned is that customers are looking for 250 metric tons of hydrogen per day or more in order to meet their hydrogen demands. So that's a significant amount of hydrogen. Because of our very small footprint and because we are carbon free, it's a perfect fit for clean chemical plants and other industries that use significant quantities of hydrogen.
Okay, so can you tell me how it's a high temperature steam electrolysis, right? HTSE, is that the process? Can you tell me how that differs from just the regular temperature electrolysis?
Yeah, so right now you think about room temperature electrolysis and what's currently available as a technology. This approach is about 30% more efficient. So you're able to produce hydrogen in a more efficient manner, and that means you can actually reduce cost. The second part of it is because it is this type of technology is also reversible. So what that means is I could produce hydrogen during the day when maybe you don't need to use as much power to the grid, store that hydrogen, and then you can run it through the same cells in reverse as a fuel cell to produce electricity. So it makes an ideal hydrogen storage, energy storage system. The challenge has been getting it close to the process that's going to use it, that's going to use the hydrogen. So in the analysis that we've shared with some different companies, they want to build a NuScale plant in the proximity of their end use, and they need it to be very compact. So they don't have thousands of acres to collect energy to produce hydrogen and then transport it. And so this provides a very compact system within less than 35 acres or so. You can actually build a 6-module plant that could produce roughly 270 metric tons of hydrogen per day. So it's a very compact footprint, and it could do it reliably. And it's not just the hydrogen, it's also oxygen and process heat that they're looking for.
Okay. I mean, that's definitely one of the big problems with this, whole hydrogen economy that we're supposed to be getting is that, up until now, all the hydrogen that was made was used right where it was made. And now all of a sudden we think that we're going to be, putting it in ships and pipes and long distance pipes and stuff like that. So is that like a key part of your point of differentiation?
It is reducing the transportation costs by having it in the proximity of the plant, because our new small modular reactor, which is the only one approved in the United States, because of its very high level of safety, it could be placed closer to these types of processing facilities and operate very safely.
The amount of land needed for nuclear is small compared to how much you'd need to generate the same amount of wind and solar, assuming that people are happy to use the land surrounding the reactor for other purposes. And I will just add that while a nuclear power plant or most solar farms generally need exclusive use of the land, wind farms and certain types of solar like rooftop or agrivoltaics can coexist with other land uses. So it's not so easy to directly compare the land needs for different energy sources. Still, nuclear is definitely more compact than wind and solar, which would be a benefit in places where there isn't a lot of land available. The other aspects that Dr. Reyes mentioned, being able to locate the hydrogen production where it's needed, that's a benefit, as hydrogen is so tricky to transport long distances. And the reduced energy consumption by using some of their waste heat to get them closer to the temperatures needed for the more efficient high temperature steam electrolysis. That will help to bring down the costs a little bit of the hydrogen, which would otherwise no doubt be very expensive if it was made from nuclear electricity. Dr. Reyes also hinted at the possibility of matching hydrogen production to suit a variable electricity grid, which takes us to the other point of added value that NuScale is aiming for, increased flexibility of output.
We've designed our plant with 3 different modes of load following, so we can work with winds and renewable. We can increase the penetration of these variable generators because we can stabilize the grid. So there's a lot of features we built into this very modern design because it's a modern grid. The grid has changed. We need to be able to adapt to that. 3 different modes of load following were developed separate and apart from the applications like hydrogen or desalination. So the first mode of load following is just steam bypass. Because our modules are small, we can dump 100% of our steam to bypass the turbine and go straight to the condenser, or any fraction thereof. And so that's for rapid changes in power. So that we did a study with UAMPS with one of their wind farms to show that we could stabilize the grid using this approach. To really build on that approach, though, you would like to be able to do some of the power maneuvering as well. And so we built that feature into it. So our 4 central control rods we can raise and lower and change the power from 20% to 100% in about 96 minutes. So the combination of maneuverability and steam bypass really gives you a very strong tool for load following wind, and it's a very good tool for load following solar.
Thanks, Dr. Reyes, for taking the time to talk to us. NuScale's SMR does seem to address many of the key disadvantages of traditional nuclear and hydrogen. To me, the most interesting aspects are NuScale's efforts to reduce costs by working to improve the safety system and to reduce development timeframes. There are other nuclear reactors already that are installed and call themselves small modular, but I believe that NuScale, if they pull it off, will be the first where most of the manufacturing is done in a factory. The others, well, yeah, they're smaller than traditional nuclear reactors. They've still been manufactured on site where labour costs are higher, timeframes are longer, and there's less opportunity to see cost decreases as more identical units are made one after the other. So perhaps NuScale will be the first to realise the potential benefits of small modular reactors, which have been talked about for ages now, but they're not achieved in reality yet. NuScale have a project underway in Utah, and we'll have to keep an eye on that and wait until the end of this decade to see whether it progresses on time and on budget. In terms of safety, the NuScale design does sound like a very different approach to traditional nuclear, and they've done the testing and actually gotten the safety approval. They're the first SMR to get US approval, with several others following behind. But as I mentioned at the start, the actual safety performance of even traditional nuclear is really not as bad as its reputation. If I look at the stats with my engineering eyes, nuclear is already incredibly safe on average. But despite this, there is so much community opposition to it, both for the safety and the waste, which NuScale is approaching in the same way as traditional nuclear. So I think the biggest test for NuScale's new SMR may not be the technology, but rather community acceptance. The small modular nature sounds like it offers excellent flexibility to locate a lot of small reactors near to demand instead of a huge centralized reactor that you need to build power lines to connect to where the demand is. But more reactors also means more people living near them. Do people want small modular reactors near their communities? Or maybe will these projects get bogged down in dozens of community consultations instead of just one if an equivalent amount of traditional nuclear generators were built? So, where do I stand on nuclear? At this point in pretty much any video, it's kind of tempting to say something like, we need to use every clean energy technology if we're ever going to solve the climate crisis. That's a pretty easy way to conclude any video about any energy technology that has both pros and cons. And guess what? That's every technology. But I won't say that, because what we need is a variety of good technologies. We don't need everything. I mean, we can manage the energy transition just fine without, say, flapping wing wind turbines or space-based solar power or solar freaking roadways. But nuclear power is different. It currently makes up a not insignificant chunk of the world's electricity generation, and it has really different downsides to wind and solar, so it can be a nice complement. I think it makes sense to consider it on its merit, and where nuclear can be achieved safely and cheaply, there would really need to be a very good reason if you were to rule it out. But I do really want to stress that even if small modular reactors do everything that we hope that they will, they still won't be ready until the end of the decade at the absolute earliest. And we need to reduce emissions faster than that. We need to reduce emissions from the electricity sector by 30 to 90% by 2030 if we want to limit global warming to 2 degrees or 1.5 degrees respectively. So it is 100% definitely not a matter of simply sitting back and waiting for new nuclear technology to mature without also ramping up renewable energy as fast as is humanly possible. So I said at the start that I don't have strong feelings about nuclear, but I know most people do, and I know that because of the huge number of comments that I get about nuclear, even on videos that have absolutely nothing to do with that technology. So now's your chance. Comment below on whether you think NuScale's reactor is going to put nuclear back in the race to a zero emissions economy. And if I left out an issue that you think is an important part of the nuclear debate, then let me know. These kinds of comments really help me figure out which topics to dive deeper into in future videos, so please keep them coming. This video topic was voted on by the Engineering with Rosie Patreon community. I asked my co-producer tier of Patreons to vote on tricky and time-consuming video topics to help me prioritize where to spend my unfortunately limited time. If you'd like to support the channel and help shape the future direction, then we would love to welcome you to the team. I'll see you on the next video.